Today we move from a discussion of rational functions or fractions to radical functions or square roots in this case. Now, a radicand is the expression under the radical sign. You'll see I have a radical expression here, and the radicand in this case would be x. We're going to take and graph some square root functions today, and we're going to start with a conversation of what is a parent function of a square root. Well, a parent function is your most basic function you'll ever see. So it's like a stripped down car with AM/FM radio, no nice tires, basic vinyl seats, etc., etc. This is the parent function, y equals the square root of x, and it's the most basic radical function you'll ever see. If I want to graph that, the only way we really know how to do that is to make up a chart and put in a set of values. And if I want nice integer values for both the x and y answers, then I have to pick numbers that are perfect squares. So I can't pick any negative numbers because I know that no number multiplied by itself, which is a square root, is going to be a negative number. So I need to start with 0. Then I get out 0. My next perfect square is 1. I get 1, 4, 2, 9, 3. And if I graph that, here's 0, 0, 1, 1, 4, 2, 9, 3. And you'll see this graph kind of arcs up, not super fast, but it moves to the right. Domain and range. Domain are all my possible x values, and my range is all my possible y values. You'll see that my x's in this graph start at 0 and move to the right forever. So x is greater than 0. And you'll see my y's also do the same. They start at 0 and they move up, and they're going to go up forever. So y is greater than 0. We're going to graph a series of radical functions, and they aren't quite as simple. Every radical function can be expressed as a form of transformations. Now, what a transformation does is it moves the graph or changes its shape in some way, shape, or form. You'll see I have y equals a root quantity x minus h plus k. X and y in this case are just coordinate points, as they always were. H is what's called a horizontal translation. It moves all the points on the graph to the left or the right. K is what's called a vertical translation, which moves all the points up or down. A is what's called a y multiplier or a vertical stretch factor. And what it does is it multiplies the y values of the function, making it taller or squishing it down. And if a ends up being a negative, not only does it make it taller or squish it down, but it takes all the y values that were positive and makes them negative. So it'll put them down in the lower quadrant over here and make the graph move from this look to this look. Now, the interesting thing about this is we're going to graph this function y equals the square root of x minus 3 minus 5 without really ever plugging points into this function itself. Because if I have to continually think about, okay, well, what when I subtract 3 from it is going to give me a perfect square, could take a while. We could do it, wouldn't be too hard, but what we're going to do is we're going to use this idea of all these graphs come in this form and are just transformed from the parent function. So what I'm going to do is I'm going to note that h and k basically translate the origin of the graph. So let's identify h and k, and a for that matter, in this function. I look in front of the radical sign and I see there's no number here. It can't be a 0 because the whole term would be 0 then. So it must be a 1. So my a value is equal to 1, which means my y multiplier is 1, and anytime I multiply anything by 1, it remains the same. So my y values will never get multiplied by anything. My h value follows the negative sign in the radical, or the subtraction sign in the radical, so my h is 3, and my k value follows an addition sign outside of the function. Well, I don't have an addition, I have a subtraction, but I know that's the same as adding the opposite, so k must be negative 5. Given that, if h and k translate the origin of the graph, then my hk value translates my origin to the point 3 and negative 5. So let's locate that on my graph. If I go over 3 and down 5, that puts me right here. Now what this dotted crosshair is it's really the origin translated down. And what I'm claiming is that because my y multiplier is 1, the shape of my radical graph is no different than the parent function. Let's take once again and look at the parent function. We know that parent function has x and y values, 0, 0, 1, 1, 4, 2, 9, 3. And if I graph those values from this new origin, I'm going to get the graph of this function here. So here's 0, 0, 1, 1, 4, 2, and 9, 3. I'm going to graph this. Like so. So again, you'll see that same arcing figure. It looks just like y equals root x. And you'll notice I've graphed this without ever plugging values into this function here. Now what I always do want to do though is make sure that these numbers check out. In fact, you'll notice 0, 0 is never graphed in this green graph here, although I use 0, 0 to draw my graph. You'll notice though, if I plug the point 3, 5 into my graph, it checks. 3 minus 3 is 0, minus 5 is negative 5. So that's an actual point on the graph. Once again, these are not points on your graph. They're just used to draw the graph from the translations. If I check another point, let's look at a point. This point right here looks to be 7 and negative 3. I'm claiming 7, negative 3 is a point on this graph, even though I never used that point and plugged it in here. Let's take 7, subtract 3, square root it, which we know is 4 rooted, or 2, and subtract 5 to that, which is negative 3. And what do you know? There's the point 7, negative 3. So this graph checks. If I wanted to find the domain and range, the domain of this graph, we see that its x values start at 3 and move to the right. And you'll see its y values start at negative 5 and move up. So that would be the domain and range of that graph. We're going to do this a number of times so we can get a hang of things. We're going to change a, h, and k values as we move along. So you'll see in this graph, it's very similar to the last one. I have a 1 in front of my root, and we need to identify our a, h, and k values. A, once again, is equal to 1. That's the number multiplied to the radical function. H is a number following a subtraction sign under the root. Well, I don't have a subtraction sign, but I can make one. I have y, and I need a plus 1. Plus 1 is the same as subtracting a negative. And then as in the last problem, we look and say, well, I need an addition here. So subtraction is the same as adding the opposite. So in this case, my h value is negative 1, and my k value is equal to negative 4. So if I move over 1 and down 4, that puts me here. And once again, this cross here is going to represent the origin translated. So our new origin is going to be negative 1 and negative 4. And my parent function, once again, is going to be y equals root x. Because of an a value of 1, it states that my y values are not going to change at all. Parent function, root x, I have x and y's, 0, 0, 1, 1, 4, 2, 9, 3, once again, and I'm going to graph these values from my new origin. So here would be my 0, 0. If from this new origin I move over 1 and up 1, over 4 and up 2, over 9 and up 3, get a graph that looks like this, and it looks like a square root function. And what I always want to do is I want to go back and make sure I check a point. I know here I have a point of 3 and negative 2, which I never used in plugging into this function, but I can do that now to make sure this point checks. I have the value of 3 going into x, so that's 3 plus 1 square rooted, which is the square root of 4, which is 2, and I subtract 4 from that, and I get negative 2, which gives me once again the point 3 and negative 2. So this point checks, which means I probably graphed this correctly. My domain are my x values, which start at negative 1 and grow larger. So x is greater than negative 1. My range values start at negative 4 and grow larger. Now you'll notice in this next graph, the only thing that is affecting this graph now is this 3, and the 3 happens to be out in front. I have nothing under my radical sign or outside adding or subtracting to my radical sign. So what this says is it says my a value is equal to 3. And because a is what we call a vertical multiplier, okay, y values of the parent are multiplied by a factor of 3. So what's that mean? It means that I look at my parent function and I multiply the y values by a 3. So here's what I'm going to do. Here are my normal x values, 0, 1, 4, and 9. And for my parent, which is root x, I get 0, 1, 2, and 3. But this problem states that I have a y multiplier of 3, so I'm going to multiply all these y values. Root x is just y, by a value of 3. So 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. So what happens now is I've created a new table such that these are still my x values, and these are my y values that I'm graphing from my translated origin. I have no translated origin. My origin is 0, 0 because there's h value equal to 0 and k value equal to 0. So I can start graphing this from the point 0, 0. I then go over 1 and up 3. I go over 4 and up 6. Go over 9 and up 9. And here's my new graph, and you'll see that it looks similar to a square root. It's curved, but it's rising much quicker. And we can plug in any of these points to this function here and ensure that they actually work. So once again, if I plug in the point 4, I have square root of 4, which is 2, and I multiply that by 3, and I get 6. And there's that point 2, 6, which checks. Now we're going to start combining quite a few of these things very shortly. We notice here our h value is equal to 0 and our k value is equal to 0. So there are no translations. And in this case, I have an a value equaling -4, and that's my y multiplier. So I take a look at x and my parent function of root x, and then I'm going to multiply my y values by -4. And once again, this column is my y column. I look at the point 0, 1, 4, and 9. Parent function values are 0, 1, 2, and 3. And I multiply all those values by -4. 0, -4, -8, -12. And now I proceed to graph from my origin, which is 0, 0, these values. Here's the point 0, 0, 1, but I go down 4. 4, but I go down 8. And 9, but I go down 12. Once again, there's the general shape of a square root. However, because I've multiplied my y values by a -4, the graph's been reflected. I can take any point and check it. Here's 4 and -8. By plugging it into this function, you take 4, square root that, which is 2, multiplied by -4, and I get -8, and that checks. So that is the point 4 and -8. Domain, in this case, is x is greater than 0, and the range is y is greater than 0. So now we're going to put a lot of this together. Let's take this function and identify all its pieces. My a value is equal to 2. I'm going to rewrite the function a little bit so it is in the proper form. I need there to be a subtraction within the radical sign. So this is x minus a negative 3. And I need an addition to be outside, so that's still okay. And now I identify h and k from here. So h is equal to negative 3 and k equals 6. So I get a new origin of negative 3 and 6. I have a y multiplier of 2. So let's find this negative 3 and 6 first. So what I'm saying now is my origin has translated from 0, 0 to negative 3, 6. And if I look at my parent function, which we again go back to and say, well, that's just 0, 1, 4, 9, 0, 1, 2, 3. All these y values will be multiplied by a factor of 2. So 0, 2, 4, and 6. Now when I graph, I'm going to graph this pattern over here from my new origin. So from this new origin, I'm going to move over 0 and up 0. From this new origin, I'm going to move over 1 and up 2. Over 1, up 2. From this new origin, I'll move over 4 and up 4. And from this new origin, I'll move over 9 and up 6. And then I sketch my graph from here. So this is the point, it's like 6 and 12. And again, I didn't plug 6 into this original function, nor did I plug 6 anywhere in over here. But I'm going to check that 6, 12 is an actual point within this function by plugging it in. So I'll take 6, add 3 to it, and square root it. Well, that's the square root of 9, which ends up being 3. Then I multiply 2 to it, which gets me 6, and add 6 to that, which gets me 12. So the point 6, 12 actually does exist within this graph, which means I probably graphed it correctly. If I want my domain and range, my x's start at negative 3 and get bigger, so x is greater than negative 3. My y's begin at 6 and grow larger. A couple more just to get a hang of things. You'll notice the a term is now a fraction, and we need to write this in the correct form, so I have y equals 1/3 times the root of x. I need a subtraction, which I have, minus 4, and I need an addition after this, so it must be plus a negative 2. And now I identify my pieces. I have an a value of 1/3, an h value of 4, and a k value of negative 2, which means I have a new origin of 4 and negative 2. I have a y multiplier of 1/3. Before we move on, I'm just remembering something. When I go back to my original graphs and we're describing our domain and range, I said these were strictly greater than. They're all greater than or equal to. So if you go back in your notes and adjust all those domain and ranges so they read greater than or equal to. We didn't do one here, but that would be a good thing. So let's go ahead and deal with this graph. In this case, we have that new origin of 4 and negative 2, so I go over to 4, down 2, which puts me here. And we have a y multiplier of a third, so again we go through and make our chart where I have x, root x, and multiplying these y values by a third. So my normal parent function of 0, 1, 4, 2, 1, 4, 9, and 0, 1, 2, 3. And all these y values are multiplied by a third, so there's 0, 1 third, 2 thirds, and 3 thirds, which is 1. So now we'll notice that from this new origin, I move over 0 and up 0. I move over 1 and up a third, which is going to be difficult to do, but you'll see where we're going. I move over 4 and up 2 thirds. And then I move over 9 and up 1. So you'll see in this case that while it's very hard to see this square root function, it still is a square root function, but it's moving up much more slowly because my y values have been pushed from their normal value to a multiple of 1 third of their normal value. And if I go once again domain and range, my x's start at 3, 4 actually, and get bigger. And my y's begin at negative 2 and grow larger. That's all we've got. Go ahead and write the lesson summary and answer these questions below, and we'll chat more about this tomorrow.